Hi everyone, my name is John Elasic and this is the power plant output model exercise. Um, so in summary, the goal of this project is to estimate the power output from a power plant uh, within, with the acronym PE using environmental readings from the plant. We've been given 4 features to go with that reading, that PE target variable. Their temperature, which will be known as AT, ambient pressure, AP, relative humidity, RH, and exhaust vacuum, V. Now, because the PE is a continuous numeric value, this is going to wind up being a supervised regression problem. And a continuous numeric value is one where the target we're predicting could take on a number within a range, not just whole numbers or categories, for example. So the output could be anywhere within a spectrum between, 430 megawatts and 495 megawatts. It's not limited to a fixed category, which we would probably use a different model for. So this makes it a regression problem because we're predicting that number on a continuous scale. It's also a supervised learning problem because the data sets provide both input features that we just mentioned and the output, which is PE. The model is going to learn by comparing its prediction to these known outputs and adjusting the minimized error. So we've chosen for evaluation metrics that are standard for regression, root mean squared error, mean absolute error, and R squared, which tell us how much of the variance and the target is explained by the model. The RMSE, or the root mean squared error, and the MA, mean absolute error, are important because they give us a sense of average size of errors in real-world units of megawatts. From an algorithm and feature perspective, we already went through the features, but I've really used 3 approaches here. The first one is linear regression, which is the baseline, as we know from our class, the simplest and easiest way to interpret for a baseline. Then there's ridge regression, which is also a linear regression model, but it prevents you from overfitting on any one of the coefficients, which is also helpful here. And then I'm also using random forest, which is better at predicting performance if these variables, these features wind up having a nonlinear relationship to PE. So I modeled the data in Python for all 3 of these. We did 70% training, so 70% of the data was used for training, 20% for validation, and 10% for test. The test was only used after, or the 10% test is only used after we've decided which model we're going to use. So the training and validation takes place on all 3 models, but the 10% test is only used on the model that winds up being the most accurate based on our validation sets. Based on what I've compiled in my Python data, I found that the random forest was the most accurate based on the R squared, the root mean square error, and the mean absolute error. And then when I tested on that model, used that 10% test data, I saw similar results to validation. So again, like I had said in the model development, each model was trained on that same 70% of data to determine the coefficients or the weighting in the case of the random forest, and then the coefficients in the case of the linear and ridge regression models. So you can see on your left the output of the model for the coefficients for both the linear and ridge regression. And then also from the random forest feature, random forest model, we were able to output the importance of each of these individual features with regard to the output. And we could see that temperature far and away has the highest impact on the target variable output, the PE. So that's something to keep in mind as we go through the results of this analysis. So I didn't really have a lot for the Python model, but I did want for the sorry for the decision tree, but I did want to at least put something in there. So I was able to work with Python to spit out one of the example decision trees. There were about 300 within the model that was generated itself, but this is just one of them as an example that was used in terms of determining the PE based on the features we were given. And here's the validation analysis results. So as I mentioned in the summary slide, the random forest performed the best across the validation set, and that's indicated by the green check. You can see that the root mean squared error, the mean absolute error, and the R squared have all come in better on the validation set than what we saw in linear and ridge. The one thing I would note again here for the linear regression and ridge is that they are the same, and that's because the PE is heavily influenced by the temperature AT, with the other variables playing a much smaller role. So because of that, the ridge really didn't have that much impact in changing the model or improving the model above what we saw in linear regression. They're actually the same. Now, I had mentioned that once I picked the model that I was going to use, the random forest model, I ran it through the 10% of test data that I held out of the training and validation. And we can see from the initial validation that was done, that we saw on the last page for random forest, the test that was run performed almost just as well with an R squared of around 9.6. Or I'm sorry, 0.96 R squared in both scenarios, MAE, and again, the R root mean squared error also within the same bounds. So random forest would be the best to use going forward, and we think that that's the best. If this company were to use a model, they should use the random forest model to predict their output. Thank you, and have a good day.